Hello everyone, my name is Jason Gregerson, and this video is going to be Introduction to Solving Linear Systems. So last time we talked about what is a linear equation. We said it was an equation that looked like this, where we had some coefficients, some variables, and this little piece on the right-hand side. So as an example, we looked at an equation that looked like this. x1 plus 1 times x2 is equal to 1. That was an example of a linear equation. We also said that if we had more than one linear equation, like these two linear equations that use the same variables, we would call this a system of linear equations. Last time we looked at an equation like this, and we did some operations. We added these equations together and did some other things to find the solutions for this linear system of equations. And we found a solution that looked like x1 equals 2 and x2 equals negative 1. We talked about how these two values satisfied both of these equations. But when we step back and look at these two equations now, what we see is we have a linear system of equations over here, but our solution also looks like a linear system of equations. So we can think about that solution process as starting with one system and doing some operations that led us to a different system, an easier system to look at and see the solutions. What I like about this second system over here is that I can see what the solutions are. It's such an easy system. x1 is just equal to 2, and x2 is just equal to 1. So we were able to solve that linear system. But at the end of the last video, we talked about what do we do in this case? What if our system starts to get large? In this case, we have 5 equations, 5 unknowns, but it could easily be 500 equations and 500 unknowns, or much, much larger. So what do we do then? And so today we're going to learn about what tool is going to help us solve these large systems. It's a tool that maybe you've seen before. Maybe you've heard of this tool before.
It is this feeling that has brought you to me. Do you know what I'm talking about? The Matrix. Do you want to know what it is?
So what is the matrix? Well, it's a tool we can use. We're going to use a matrix to simplify our notation to assist us in solving these large systems of equations. So as was asked, what is a matrix? Well, in general, a matrix in mathematics is just a rectangular array of values. So for us, it's really just a box of numbers. That's how we're going to see it as. And we have two examples of matrices right here. One's right here, and one's right here. Now, as we can see in these examples, they're two different sizes, and the size is based on the number of rows and the number of columns in the specific matrix. In fact, as notation goes, I might call a matrix A, and I might write how many rows it has and how many columns it has. So this first number will indicate the number of rows. The second number will indicate the number of columns. And I will call this matrix A 2 by 3 matrix. And if I want to write the specific values in this matrix, a lot of times if I'm talking about elements of this matrix, since I'm calling the matrix A, I'll use the lowercase a to talk about the specific pieces. I'll say this is the number that's in the first row and first column. This could be the number that's in the first row, second column. This could be the number in the first row, third column. This would be the element in the second row, first column, and so on and so forth. And so this is the notation I might use with my matrix. So this is an example of what a matrix is. Now, how are we going to use it to solve our linear systems? Well, this is the system that we looked at earlier. And we said that we started with this system and we did some operations, some stuff to it to find an easier system. Well, now I want to take the information that's in this linear system and express that information in terms of a matrix. So when I do these operations, if I were to add these two rows together, the things that would not change are the fact that I have two variables, x1 and x2. So those are standard throughout the whole equation. Even in the final state, where I just see x1 equals 2, I could really see that as x1 plus 0 x2 equals 2. So I really could see both of my variable values in that last equation. So I don't want to write that in every step along my process. So what I'm going to do is I'm just going to write the coefficients of my variables here. So for this first equation, the coefficients would be 1 times x1 plus 1 times x2. And the second equation, the coefficient would be negative 1 plus 1. So negative 1x1 plus 1x2. And so I could just stop here for this little matrix that has the coefficients as its values, and I would call this the coefficient matrix for this linear system. But of course, that right-hand side of this linear system is important also. So I might want to add this piece. I might want to augment my coefficient matrix with this extra piece of information, in which case I'm going to write those coefficient values, but I will write a separate piece to the right here with those values from the right-hand side to kind of make an extended matrix. And I'm going to call this the augmented matrix. So now I've taken all the information of my linear system and I've captured it in this augmented matrix. And now what I want to do is I want to take this and do some operations on my matrix to lead me to my solutions. Well, I can see what my solution will look like if I write out this linear system in terms of its augmented matrix. Well, the coefficients of the first equation would be 1 times x1 plus 0 times x2, and that's equal to 2. And the second equation would be 0 times x1 plus 1 times x2 is equal to negative 1. So somehow I need to start with my augmented matrix that represents this first linear system and do some stuff, do some operations to that system and transform it into this final augmented matrix, this new system where I can clearly see what the solutions to the system are. So I need some operations that I can perform on the first system that don't actually change the values of the solutions. So what can I do? What are these operations? We're going to talk about the 3 operations that we're allowed to do here, and we're going to call them elementary row operations. And so they're listed here, and they're listed in your text. The first operation we're allowed to do is replacement. We're allowed to replace a row by adding multiples of rows together. We're also allowed to interchange rows of our matrix. We're also allowed to scale the rows or multiply all the entries in a row by a non-zero constant. And so what do these operations look like, and why are we actually allowed to do them? Well, let's think about it in terms of our system. So if I'm solving this first system, how am I going to go about finding the solution? If I'm just solving the system, the first thing I would do is add these 2 equations together to get a new equation. If I added these 2 equations together, I would get x1 plus a negative x1. That would give me 0x1. And I would take x2 plus x2, and I would get 2x2. I would get 1 plus a negative 3, which would give me a negative 2. And the idea is if I'm adding these 2 equations together, if the left side is equal to the right side of the first equation, and the second equation, the left-hand side is equal to the right-hand side, if I add them together, then I should have another true statement. I shouldn't have any new information because I've just added 2 true things together. And so this is a third equation for this system. But it's not really adding any information. But I could use it to replace one of these 2. I only need 2 equations that are giving me all the information. So I could talk about this system. And because that second equation, I don't need to write that 0x1 anymore, hasn't really changed anything, I just got that from adding the 2 previous equations, the solutions to this linear system have to be the same as the solutions of this linear system. Now what does that look like in terms of the augmented matrix? Well, what we did here is we added these 2 rows together to get a new equation that looks like this. So what I'm going to do with my augmented matrix is I'm going to use that first row operation. I'm going to get rid of row 2. I'm going to replace it by what I get when I add the 2 rows together. So I'm going to need a new R2, and this is my notation to represent this row operation. I'm going to get a new R2. And what is the new R2 going to be? It's going to be the result of taking R2 and adding R1. My new row 2 is going to be the result of adding the 2 rows together. And well, I don't change row 1, so I'll just write those values out. And the new row 2 will be, well, if I add these together, I have 1 plus negative 1. That's 0. 1 plus 1 is 2. And 1 plus negative 3 is negative 2. So we can see that doing this row operation is exactly the same thing that I've done with the equation. So it makes sense that I can add rows together because I can add equations together. Similarly for the second one, I can interchange 2 rows because what does that look like in terms of the equation? It looks like just switching the 2 equations around. Of course, that doesn't change the value of the solutions, so that shouldn't change anything here. So what's the next? The final operation is scaling. Well, I would use that if I was solving this linear system. My next step in finding the solution, I'm going to leave my first equation the same, but I want to solve the second one for x2, so I would divide both sides by 2, or I'd multiply both sides by a half. The result would be x2 is equal to a negative 1. I've taken that equation and just multiplied it by a half, and I'm allowed to do that. Well, that's the same thing as multiplying a row of my augmented matrix by a half. If I take R2 and say the new R2 is going to be 1/2 of the old R2, I'm just multiplying that row by a half. The result would be, row 1 hasn't changed, so I will just write that out. And I take 0 times the 1/2 is 0, 2 times 1/2 is 1, and negative 2 times 1/2 is negative 1. And once again, I can see that's the same as my equation above. Now to finish solving this set of equations, you might take that value for x2 and plug it into the first equation. But another way to think about that process is I could take this equation and subtract this equation. If I did that, I would have x1, I would have x2 minus x2 would be 0 x2s, and I would have 1 minus a negative 1, which would be 2. So I would get exactly this expression. I would get x1 equals 2. And I can do that same process below. My last step would be to replace the R1 row. Take R1, and the new R1 would be R1 minus R2. And that would exactly get me to this last expression. So the bottom line is I can take my system of equations, I can represent it with an augmented matrix, and I can do elementary row operations. And as I do those row operations, I get new systems, but I haven't changed the solution. I've only done operations I'm allowed to do. So to summarize those key points, we're going to introduce some terminology. It says two matrices are row equivalent if they differ only by row operations. So if I start with an augmented matrix and I do a row operation to it to get a new augmented matrix, because those row operations are just adding equations together or interchanging equations, they're not changing the solution set. I'm going to call these two matrices row equivalent. And then it says if two augmented matrices, if the augmented matrices of two linear systems are row equivalent, then the systems have the same solution set. So all this says is that I'm allowed to do these row operations to find an easier system, and I'm not changing the solution set. All right, let's look at another example. So now I have a bigger linear system. This is one that might be hard for me to do by hand, but I'm going to follow the same steps I did before. I'm going to translate this into an augmented matrix. So I look at that first equation. It says 1 times x1 plus 0 times x2 plus negative 3 times x3 is equal to 8. And in the second equation, I get a 2, 1, negative 6, and 6. I get a 0, 1, 2, and negative 2. So I've created this augmented matrix. Now, my goal is to solve the system to find the solution. It's to get x1 equals to some number, and x2 equals some number, and x3 equals some number. That's what I want to get in the end. And so if I think what the augmented matrix for this solution would look like, it would look like, well, if my first equation was x1 equals some number, that would be 1 times x1, 0 x2, 0 x3 equals that first number. And the second equation would look like 0 x1, 1 x2, 0 x3, some number. And the last equation would be 0, 0, 1, and that third number. So that's what the augmented matrix for this nice clean solution would look like. So I've started with this augmented matrix, and now I have to do my row operations until I can get it down to this form. And that's the solution process. So I have a 1 right here. I want a 1 like that in my final answer. So I'm just going to leave that one where it is. But I don't want this 2 here. I need to get rid of that 2. So to get rid of that 2, I'm going to use my 1 to get rid of this 2. I want a new R2 that doesn't have the value 2 there, but has a value 0 there. So I'm going to take my new R2 to have that second row minus 2 times the first row. Because that first value, that first position value in the first row is 1. If I take that 2 minus 2 times that 1, I should get a 0 in its position. So I'm taking the second row minus 2 times the first row. This value minus 2 times this value. That is 0. So I'm not changing my first row at all. So I will simply write those values in. I'm taking the second row value minus 2 times the first row value. 1 minus 2 times 0 is just 1. Minus 6 minus 2 times minus 3. Sometimes I'll write these values out so I don't mess up my addition. So negative 2 times negative 3 is positive 6. So I have negative 6 plus 6. When I add those together, I get 0. This last one, I get 6 minus 2 times 8. So I have minus 2 times 8. That would be minus 16. 6 minus 16 is a negative 10. And I'm not changing my third row values at all. So that process of adding multiples of rows together allowed me to eliminate this 2 value. So now over here I have my first one. I've got my second one along what's called the diagonal of this matrix. Now all I have to do is get rid of this value right here. So to do that, I'm going to need a new row 3. My new row 3 is going to be R3 minus R2. So I'm not changing my R1 value. My row 1 stays the same. My row 2 stays the same. But now I'm taking the third row and subtracting the second row. So 0 minus 0 is 0. 1 minus 1 is 0. 2 minus 0 is 2. And negative 2 minus 10 is positive 8. So I'm getting very close now to what I want. This is what I want over here. Now I got to get rid of this 2 and turn it into a 1. One of my row operations says that I can scale a row. I can multiply a row by a number. So I want to get a new R3 and take my old R3 and multiply it by 1/2. When I do that row operation, once again, my first row stays the same. My second row stays the same. My third row gets multiplied by 1/2. I'm almost done now. Now I just have to get rid of this negative 3. So I need a new R1. It's going to be R1 plus 3 times R3. I'm using this 1 to get rid of that negative 3. So I'm not changing R3. I'm not changing R2. I am changing R1. R1 plus 3 times R3. 0 plus 3 times 0. Negative 3 plus 3 times 1 is 0. And 8 plus 3 times 4. That's 8 plus 3 times 4. 8 plus 12 is 20. And so because I've just done row operations, I know that the solution to my original system should be the same as the solution to this system. But if I write this augmented matrix back into equation form, well, the first equation would be 1 times x1 plus 0 times x2 plus 0 times x3 equals 20. The second row would tell me that 0 times x1 plus 1 times x2 is equal to negative 10. And the last row tells me x3 is equal to 4. So from this system, I can clearly see what the solution is. So I took my system, I wrote out the associated augmented matrix. I used my row operations to get down to this simplified form, and then I could see my solutions. In this case, I have one unique solution. My solution is x1 equals 20, x2 equals negative 10, and x3 equals 4. Now, if you recall, in our last video, we said that linear systems could have one solution, they could have no solutions, or they could have infinitely many solutions. And we should be able to see those same results from our augmented matrix. So, if I look at these two systems, so if I have linear systems, and these are the associated augmented matrices, I would say, what are the solutions to these systems? Well, if I took this first one, and I wrote out the associated equations, I would get x1 plus 2x2 plus 3x3 equals 4. The second equation would be 1x2 minus 2x3 equals 3. But the last equation would tell me 0x1 plus 0x2 plus 0x3 is equal to 2. But that's impossible because this says that 0 equals 2. Therefore, there must be no solutions to this system. We would call this system inconsistent. That's the terminology we would use for this if it does not have solutions. In the second case, we basically have the same first two equations, but our last two equations, our last row gives us the equation 0 equals 0. And we say, well, when is that true? Well, that's always true. And so if we were able to finish up the solution, what we would have is later what we'll define as a free variable, but it tells us there will be infinitely many solutions. There will be infinitely many solutions. That's the case we'll be in here. Now, whether there are infinitely many solutions or just one solution, in either way, we call that a consistent system because it has solutions, whether there's one or infinitely many. So we can see all those same solution cases by looking at the augmented matrix, just like we could look at the actual equations. All right, and that concludes this video on solving systems of equations.